All right, chapter 3, equilibrium of a particle. We're going to look at particles or systems of forces that are concurrent to a point in 2 dimensions and in 3 dimensions. Both cases, the equilibrium condition is for the vector sum of the forces to be zero. This stems from Newton's first law of motion. Um, and So yeah, if the sum of force upon a particle are all zero, it means the particle will be at rest or moving with constant velocity. Any unbalancing force causes acceleration. That's the second law of motion. So non-accelerating, meaning that A is zero, meaning that sum of force equals zero. Okay, so essential in solving equilibrium problems is to draw what are called free body diagrams. So we're going to delimit the shapes of bodies of interest and show the effect of the surrounding bodies by as forces. So for example, if we have a spring that has a mass hanging at its end, a vertical spring suspended and a vertical mass, we're going to show the weight that body acting at the end of the spring, causing it to increase length. If we measure this change of length S from the free length of the spring, SL0 that is, and for linear elastic springs, this force developed by the spring would be equal to spring constant or spring stiffness, the property of the spring, times that deflection measured from equilibrium. We can also have springs that are in compression. In that case, forces will be reversed, and redefining the orientation of force and deflection, same equation would apply. For cable and pulley systems, we're assuming, coming back just a little bit, so springs are assumed to be ideally linear, firstly, and massless. For cable and pulley systems, we're assuming cables to be ideally flexible and massless, and then pulley to have negligible friction. So equilibrium of a system of rope running over a pulley like this one requires for the tension in the two branches of the cable to be equal. And then we can have smooth contact. Given here as an example, so you have a disc that's in 2 dimensions that is pulled by a cable. It's the tension T in the cable. We have some geometric information. So this angle, that angle. When we do free body diagram of just the disc, we show the tension of the cable, the weight of the disc. This is assumed to happen in the vertical plane. And then the effect of the incline upon the disc is this normal force. Okay. And a review of the approach. So drawing free body diagram, you remove supports. Example is this bucket here suspended by a cable. So we have the weight of the bucket and the tension in the cable, free body diagram for just the bucket. And equilibrium condition requires for the tension of the cable to be equal to the weight of the cable. So yeah, free body diagram requires to isolate the body and show the surroundings. Depending on what we're after, we may limit the the amount of the effect of the environment. So for example, a complete free body diagram for this cable pulley system would require to show the effect of the, say this is a ceiling upon the pulley mount, but it's not shown there. Purpose is just to show how this the tension of the cable is deviated by the pulley to a different angle. Okay, so yeah, show all active forces and the gravity, including if it's a problem happening in vertical plane, and then write the equilibrium conditions. An example here was a heavy disk that's suspending with two bungee cables. Due to symmetry, the weight of the disk is acting at the geometric center. So free body diagram of the disk and the tension in the two bungees and the weight of the disk itself is shown to the right. If we have an example with numbers, so if we have contact, say this ball is touching in 2D, we can assume this to be a disk, but appears to be a sphere based on the illumination. So we have the two planes, and we're going to show the normal forces acting at the contact between the body and the two planes, and then the weight, and then we have the tension in this portion of the cable CE, and so that's shown here, and then a free body diagram of just the although sometimes can be trivial and we skip it. So yeah, free body diagram of the cable CE, and then free body diagram of the knot at C. Okay, so the corresponding equations for each are used towards the solution. And I mentioned them already, but it's only here that they are is discussed. So coplanar force systems, how do you take this equilibrium equation and turn it into, as you'll see, scalar equations you can solve algebraically. So in 2 dimensions, a vector equation has this equivalent, and so for this to be equal 0, it has to be 0, the individual sum of components over x and y axis, which is equation 3.3. And important to remember that 2 scalar equations can be solved for just 2 unknowns. Those could be 2 magnitudes of forces, could be force in some angle, or could be other geometry information only if all forces are given. So yeah, choose the proper reference frame, show the forces, identify unknowns, see if you have enough information to solve for no more than 2 unknowns, and proceed with the solution. Important to know, so if any unknown force was assumed, well, we need to take some orientation. Sometimes it's obvious, sometimes it's not. So if from the solution the magnitude ends up being negative, it means that their respective force has to be reversed, change orientation. All right. So yeah, some examples. You have a equilibrium of a particle, 2 forces acting, one assumed in the positive direction. From calculations of the F being negative, it means that we need to reverse it for equilibrium. Okay, so don't forget solving, or rather drawing correct free body diagrams, and then stating equilibrium equations. You cannot solve for more than 2 unknowns. Some numerical examples. So geometry given, the weight of body D given, free body diagram is just the body, and then free body diagram of the knot. We don't know the tension in these 2 cables, but we have geometric information, angles, and we can state the sum of force in x and y. I can solve for the unknowns. Other problems they have in geometry is unknown. So here, what would be the angle for which, by pulling force not known, will max the tensile strength capacity of cable AC, which is 10 kilonewtons. Right. So again, in this case, we have geometric information that is unknown with a force. And here it shows the case with the spring, again massless, the distance, horizontal distance C to be known. Question is, what is the length AC with this having to be 30 degrees, that will um, yeah, so that and the mass of the lamp is given with the free length of the spring and spring constant. So yeah, if we can set it into this arrangement, right? So free body diagram of the knot was all that was given, and stretch length of the spring plus the projected uh, uh, the projected length AC over the x-axis, the two together make for 2 meters. Okay, and yeah, we'll try to do as many problems as possible, and I'm moving to the case um, of 3 dimensions. So here it said 3-dimensional force systems could be equilibrium of a particle in 3 dimensions. So the same vector equation, this time expressed relative to 3 axis. So we have sum of forces equivalent to the vector equation is sum of force in the x equals 0, sum of force in the y equals 0, sum of force in the z equals 0. So the thing that we learned in chapter 2 had to go and be applied for this kind of problems. In the 3-dimensional case, having three independent scalar equations, we can solve for at most 3 unknowns. Again, could be magnetic forces or could be some geometric parameters, some angles or distances, and so forth. Okay, so it starts with choosing a proper reference frame, usually the z-axis, the vertical axis. We have gravity acting in the negative direction of z, and yeah, state equilibrium equations, and solve for the knowns uses as much additional information from the geometry given for a solution. Okay, so yeah, and some sample problems, as usual, I encourage you to go over them. And I guess this is it for this chapter.